is dealing with the loan default prediction, the lending default prediction, and what ML is going to do about it, then the data integrity and leakage defenses. And we looked at 3 leakage types. Basically, these are what you're going to see in the presentation. I have the model architectures here, the logistic regression. Since it's a numerical project, it's always best to first use the logistic regression to get the accuracies and then continue with the rest of the models. So I had the logistic regression, random forest, the XG boost. This is where I ended last time. So I've added the tabnet and the tab transformer. So to dive into my presentations, what is this module doing? This module, the application gatekeeper, as I shown you here, the application gatekeeper is before any money is dispersed, it estimates the probability that a borrower will default, enabling the approve, review, or decline deposit decisions. Okay, I won't use many words, but as you can see, this feature, it's like an askari. It closes up if someone is able to default. As you see here, that the features, it's everything known at application time. We get to know the loan amount you want, the duration you want it in, the district and the business type, and the application and the applicant age. Then its target is to get to know that this is the feature X and then this is the target Y. You get to know that if the borrower is going to default, it is a 1. And if it's going to be, if the borrower repaid, it's going to be a 0. And the decision here, the threshold converts the probability. The threshold converts the probability, the binary to the binary. Sorry, I'm trying to remove this and you see. So what the threshold does, it converts the probability to the binary action, then it approves. If the P is less than T, else it flags or rejects. I guess you can understand that. I'll take back this and this as well. So this is the this is the procedure. The application received that someone wants to get a loan, then the feature extraction. Here we get the features, what the details of the applicant, then the risk score computed. We get to know the risk score here. Then we get the threshold here when it converts the probability, the binary, and then carries out the decision output. It either flags or it rejects. So I will continue to the next slide. The next slide shows the 3 leakage types we defend against. So here we are going to look at a post-outcome proxy leakage. This post-outcome, it features that only, it shows that the features that can only be known after the loan is dispatched, like the repayments, the arrears, the penalty, burden, and balances. And how to fix this leakage, we pattern-based column drop, like we drop some columns, and then when you continue to the second leakage, the second leakage type is the global target encoding leakage. Here, the problem we look at is the district or circle encodings, which are computed using the full data set before splitting leak the label in 2 features. And the explicit drop of this is, it includes the district encoded, the source circle encoded, the business type encoded, and scaled variants. So here, the solution is to re-encode only inside the train fold using the K-fold target encoding. Then the third is the institution memorization. Here, the problem that we look at is the model learns the circle identity, not applicant risk. No, we look at the circle identity, and if same circle appears in train, and then we continue with the testing. And how we fix this, we use the circle disjoint group shuffle split. Here, there is a zero overlap of source circle across the train or valuation or testing. And the flagging here is the source circle is dropped from the feature matrix X. And here, this is part of the gist of the presentation. Why we chose the F2 score. Okay, in the F2 score, we recall the weighting and the beta is 2. Here we catch a defaulter, like the matters 4 times more than avoiding a false harm. Not to take you through a lot of details, we'll look at the threshold tuning policy. Here in the tuning policy, the model is trained. The first step, we train the model on trained circles. Number 2, we predict the probabilities on validation set. Remember the probability that we looked at in the module 1? We carry out the probabilities here. Then we continue to the sweeping of all the thresholds. Remember, we say that the target is 1 and a 0. For the 0, it shows that the borrower can repay. And then for the 1, the borrower has defaulted. So we compute F2 at each. Then we choose the threshold and the T, this is the formula, the argument maximum of the F2 score, and we validate only. And then the 5th step is to freeze the threshold. After that, we continue to the 6th step, and it is to evaluate test set once using the frozen threshold. And here it tells us that we should never tune threshold on test. That is cheating. Sorry. I have the 5 modules here. We say that we should add 2 modules, but given the fact that we should have 4 modules, but given the fact that this project is limiting us to some modules, so I just did an add up to the 2. At first, I had the logistic regression, and this one, it gave me results that the rank is eligible, and it split 6. When I continue to the decision, okay, basically the logistic uses a linear equation to train the data, and the interpretable scorecard is it was around 97.3 there. No, it was 95% the accuracy. And then when I continue to the random forest ensemble, this one used 100 decision trees, and it gave me a rank eligible to 6 splits. And then I went to the XGBoost, and this was the winner. And when I evaluated, it showed me that the rank eligible was also in 6 splits. And the highest test was OPRIC. And today I added the tabnet. The tabnet is it's a sequential attention masks, and its instance is it's a wise feature selection. It's an instance-wise feature selection. It has a number of steps, which are 4, and it has a number of the decisions as 32. And the results were promising, not stable. Then I had the tab transformer, and it had promising results as well. I'll proceed because of time. So when I went to the masking, this is how the selective spotlight works, the sequential attention. In step 1, it shows that masking brings scars all 90 features. And then the sparse max bouncer crashes weak features to 0, elevating 2 to 3 to 1.0. Okay, like there are some features that are contained in the circles, like that are not okay, that will not work for us in the modeling, in the training. So this mask, it crashes, this sparse max bouncer crashes the weak features, like like some details we pick from the borrower. Then we have steps 2, which is the evidence, where we have that with step 1, evidence is banked, the spotlight shifts. A different subset of features is spotlight for additional risky signal. And then on the third step, all the step votes are summed and pushed through the sigmoid to produce a final default. So here, the results show that only strong variable scores, but unstable across circles. Therefore, I continue to, this is just the validation lottery. And so I wanted to explain what I tested and what I found. What I tested the permutation importance, and here top features aligned with the application time logic, and no ID field cost catastrophic performance collapse. I didn't get any collapse in the features. And then I had the sharp global importance. Here we had the top features, and they were borrower loan, count, then the loan duration days, is repeated borrower, the loan interest, the up month cost, the cost interest, and the burden scaled is gone. Those are the top features that I used. Then to remove the suspicious features, some that were dropped, we dropped the branch ID, the loan product ID, marginal delta only, and we dropped and I dropped the circle columns. Those were unnecessary. Then I also had some duplicates, and I also of course this sorry, there are some duplicates that you just have to eliminate. And then I looked at the strict casual feature set versus the full, and in the stricter it sets produces realistic, and we had defensible performance and did not collapse to random. Then the warning came to the adversarial validation and its training versus testing, and the detectability was on 0.97 to 0.98, and it indicates that extreme circle distribution shift, therefore with deploy with monitoring. So in conclusion about the models, the XD boost was the winner. The reason for the winning, it's because it has the highest mean test for the F2 score, and then it has the lowest standard on tests on the F2 score test. It was the ranked eligible by the protocol. Then it handles complex tabular interactions that linear models miss. Not to waste time, I'll move to the MVP to production. Here, because of time, I want to take this very fast. We have the phase 1, which is the shadow mode. Here in the shadow mode, you run model in parallel with current process and log all predictions and outcomes. We do not change any real decisions, and then we track per circle metrics and drift daily. Then in the second phase, we use model to prioritize manual review. And then we route high risk to senior receivers. The humans remain in the loop for all decisions, and we calibrate thresholds per circle tire. In the third phase, only monitoring after proves stability. We automate declines and approvals at agreed thresholds, as we saw the threshold policy. Then we stabilize per circle performance. We confirm the stable circle performance. And then we calibrate the probabilities, and then the ongoing monitoring and drift alerts in place. So here it's how to push the performance further. And the key takeaways here is that XG boost is the best stability across the repeated circle disjoints. And then the F2 score is our compass, like it recalls the weighted metric and it aligns with the lending policy. The core ML problem here, the problem was about detecting the defaults. So what we are doing is to know everything known before money is dispersed. We know the loan amount. These are the features involved, like the major features involved before we issue out the loan. And then the target is that the borrower, what we predict is that the borrower defaulted, failed to pay, or the borrower paid, as we saw in the first slide. This was the key. And then it shows the historical labels that allow supervised learning. Therefore, the model learns patterns linking X to Y. And then we have the model output, which is the probability score. As you can see, the computation and the probability from 0 to 100%, e.g. applicant A has 15% risk, likely, safe. So if this one, the applicant has 15%, it means we can issue out the loan. But if the applicant B has 82% risk, this one is likely to default. So we also computed the threshold, and I came up with the results. Okay, when I use the threshold, it shows it's either flags or rejects. And the analogy behind is that the model is like a thermometer. The threshold is the medical fever rule, and too high means miss sick patients, and too low, it means treat healthy ones. So it easily helps us to know that default rates, the potential defaulters and those that can pay. And then what is the leakage? Here is why we actively fight it. The leakage comes in through the post-outcome proxy leakage, and then the global target encoding and institution micro memorization. Why random split fails and how group split fixes it. So I'll explain this very, very fast. The problem with random split is this, that a standard of 80 by 20 random split scatters borrowers from circle across both train and test, and the model memorizes institution and characteristics, not applicant risk profiles. Remember the applicant risk profiles, the loan duration, the borrower, the applicant age, those things, they really matter a lot. The business type, they matter a lot, but the problem is that the random split does not cater for them. But now, how the disjoint group works, the disjoint group split works, it trains the circle. We get like 4 models, 4